Hello, and welcome back to my course, How to Solve Circuits the Right Way Once and for All. It has been 2 years since I last shared with you the joys of circuits analysis, and this is going to be the last lecture of this course. These lectures are based on my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. In this lecture, I'm going to introduce the extra element theorem for 3 and 4 elements using the following examples: a passive RC circuit with voltage gain and a cascade MOSFET amplifier. As for the n extra element theorem, I'm going to have to ask you to read my book because the derivation, though not difficult, is too long for a video presentation. The first example is a passive RC circuit given by James Holbrook in his book Laplace Transform for Electronic Engineers, in which he showed that a passive RC circuit like this one shown here can exhibit voltage gain. Now at first this looks counterintuitive simply because you cannot have a flat gain larger than unity with any combination of resistances in a frequency band where the capacitors have effectively dropped out. This is certainly true for ladder networks. Now Holbrook showed that for bridge-type circuits like this one here, and with the proper choice of the circuit elements, it is possible to have narrowband peaking in the voltage gain. Now to see that this is a bridge circuit, look at R2C2, which forms the left arm of the bridge, C1R1 that forms the right arm of the bridge, and R3C3 forms the bridge element. Now I should say that Holbrook synthesized this circuit, and he did not simply stumble across it while analyzing a whole bunch of circuits. I am, however, using this circuit to demonstrate the 3 extra element theorem simply because it is an interesting one. Once we have obtained the transfer function, we will spend some time trying to determine the relationship between the element values that will result in a resonant type peaking in the voltage gain. We begin by taking out the 3 capacitors to determine the reference circuit and its gain. Now there are several different ways of taking these capacitors out. One way that is shown here is to take C1 as a short circuit, while C2 and C3 are taken as an open circuit. Another choice would be to take C1 and C2 as short circuits and C3 as an open circuit. Yet another way would be to take C1 and C2 as open circuits and C3 as a short circuit. In all these 3 different cases, the reference gain is non-zero. Now notice that if you were to take all 3 capacitors as an open circuit, the reference gain would be 0. So, for this choice of reference gain, C1 short, C2 open, and C3 open, we see that that reference gain is unity. Vin appears at this node here, while there is no voltage drop across R3 because there is no current flow through it, and therefore the output voltage V naught is the same as the voltage here, equal to the input voltage, and the reference gain is unity. We now invoke the 3 extra element theorem for the impedance elements Z1, Z2, and Z3 in the same manner as the 2 extra element theorem. That is to say, we write the transfer function AV of S equals to the reference transfer function, or the reference gain, followed by a normalized numerator and a normalized denominator, in each of which the elements Z1, Z2, and Z3 are reinstated first one at a time, then a pair at a time, and then finally once with all 3 taken together. All the calculations in the numerator are performed with the response of the transfer function null, and all the calculations in the denominator are performed with the excitation set equal to 0. We begin in the numerator by reinstating z1, and here it is. z1 sits in the little numerator, since in the reference circuit it was taken out as a short circuit. It is accompanied by the null resistance looking into port 1, that's the port across which z1 was connected, with the other two ports in their reference states. Now we substitute for z1 1 over sc1, and we obtain this expression here. Then we reinstate z2. Since that was taken as an open circuit in the reference circuit, it appears in the little denominator, and it is accompanied by the null resistance looking into port 2, while ports 1 and port 3 are in their reference state. We substitute for z2 1 over sc2, and we obtain this expression. And then finally, we reinstate z3, and since that was taken as an open in the reference circuit, again it appears in the little denominator here, and this is the null resistance looking into port 3 with ports 1 and 2 in their reference state. Substitute for z3 1 over sc3, and you get this expression. And now we're going to bring them in a pair at a time. z1, z2, z1, z3, and then z2, z3. The order is not important, that is to say z1, z2, or z2, z1. That doesn't matter. So let's bring in z1 and then z2. When we bring in z1, it's just like it was in the case where it was by itself. But when we bring in z2 next, that is to say we pair the second port with the first port, this time the impedance that accompanies the impedance element z2 is the null impedance looking into port 2, but this time with port 1, that is to say the port with which it is being paired with, in the opposite state of its reference state. And that's the difference between this term here and that term there. This here is the same as that one. Next, we reinstate 1 and 3 together. 1 comes in as it was again, as though it came all by itself. Then it is being paired with 3. When 3 comes in, the third element comes in. The null impedance looking into port 3, again, is going to be computed with port 1, the port with which it is being paired with, in the opposite state of its reference state. And the same goes for pairing 2 with 3. And then finally, we're going to bring all 3 together at the same time, and the order in which we bring it is not important. z1, z2, z3, z2, z1, z3, z3, z1, z2, whichever way you bring them in. So when we first bring in z1, it comes in just like it was here all by itself. Then we bring in the second element just like it was here in this pair of 1 and 2. Looking into port 2 with port 1, the port that it is being paired with in the opposite state of its reference state. Now when we bring in the third element and we pair it with the first and the second elements, now the null resistance looking into port 3, the port across which the third element is connected, is computed with ports 1 and ports 2 in the opposite state of their reference states. And that's the contrast between this, and between this and this here. We repeat the same thing in the denominator, except all these port resistances looking back into the network are computed with the excitation set equal to 0. So each impedance element comes in once at a time, and the resistances are the driving point resistances looking into the network from the ports where these elements are connected, with the excitation set equal to 0. These are ordinary driving port resistances. And then you pair them just like this, and then you take all 3 together at the same time. Now you can imagine what is the extension of the 3 extra element theorem to the 4 extra element theorem for the 5, on and on and on and on. So next we're going to be computing all these port resistances. We now proceed with the determination of the null port resistances in the numerator n of s. We begin with the script R1, which is the null resistance looking into port 1 with the response V naught nulled, and each of the other two ports 2 and 3 is in its reference state. Recall that you can always null a response with two excitations by setting the magnitude and phase of one of the excitations with respect to the other in such a way as to cancel the contribution of the other source to that response. Having said that, we see that R3 is looking into an open circuit, and therefore there is no current flowing through R3, which means that the voltage drop across R3 is equal to 0, which means that V0 appears directly across R1. But since V0 has been nulled, it means that the voltage across R1 has been nulled, and as a result, the current through R1 has been nulled, which means that IT, which is the sum of the currents in R3 and R1, has also been nulled. That means that the null impedance looking into port 1 is infinite. Vt over It goes to infinity when you null the response V0. Now in this case it's very easy to see how Vt and Vin were adjusted in magnitude and phase to bring V0 equal to 0. You see that the voltage between this point and this point here, the voltage across R1, is the sum of the voltages of Vt and Vin. And that means that the way this was nulled is that you made the magnitude of Vt equal and opposite of Vin. Next, we determine the null resistance looking into port 2 with the response V0 nulled, and each of the other two ports, 1 and 3, in their reference states. The reference state for port 1 is a short, and the reference state of port 3 is an open. Now, as before, R3 is looking into an open circuit, which means that there is no current flowing through it, which means that V0 appears directly across R1 as before, which when you null means that the voltage Vin must be set equal to 0 to achieve that null, since the voltage across R1, in this case with port 1 short, is the same as the input voltage. So nulling V0 in this case means that you set Vin equal to 0. And when you do that, you realize that Vt, the test source connected across port 2, appears directly across R2. And therefore it follows that script R2 is simply the resistance R2. And now we determine the null resistance looking into port 3 with the response V0 nulled, while each of the other two ports, 1 and 2, in their reference states. The reference state of port 1 is a short, and the reference state of port 2 is an open circuit. You can see now that whether the response is null or not doesn't matter, simply because this part of the circuit, R3, R2, and Vt, form a loop entirely independent of the remaining part of the circuit, which is nothing more than R1 in shunt with Vin by virtue of port 1 being a short circuit. So you see that R3 in series with R2 in series with Vt forming a loop standing on its own, regardless of what V0 is doing, which means that script R3 is nothing more than R2 plus R3, since Vt over It is R2 plus R3, regardless of what V0 is doing, as we said. And that's perfectly fine. We now substitute each of these null impedances in the numerator of the extra element theorem, where each of the impedance elements is reinstated one at a time. So, for the first one, 1 over SC1, which is accompanied with its null impedance looking port 1, which is infinity, drops out. For R2 and R3, which are given by R2 and R2 plus R3, we obtain this expression here. Next, we determine the required null resistances in those terms corresponding to two ports taken together at a time. We showed that when we pair two ports at a time in the numerator, we get the following expression, which means that we now have to determine each of R21, R31, and R32. We now determine the null resistance looking into port 2 with port 1 in its opposite state and the response nulled. The reference state of port 1 is a short, so when you are determining script R21 in this case, you have to open port 1. Now this circuit presents a bit of a problem because you see that V0 is always a 0 regardless of what Vin or Vt is doing, because there is no path from either excitation to the response. You can remove that confusion very easily by introducing an arbitrary resistance across port R1. And now you see that when you null the response V0, in the presence of this arbitrary resistance, you are nulling the voltage as before across R1, since there is no voltage drop across R3, which means that there is no current now through either R1 or R3, which means that there is no current through this temporary resistor R that you're introducing, which means that the voltage at this node is the same as Vin. So whatever value of resistance you put here, nulling the response would mean that you have to set Vin equal to 0, so that Vt as before now appears across R2, and regardless of what value of this temporary resistance is, that null resistance R21 equals to R2. So the null resistance looking into port R2 with 1 open or any resistance connected across it is always R2. We now determine the null resistance looking into port 3 with port 1 in the opposite state of its reference state and port 2 still in its reference state. Now, the reference state of port 1 is a short, so in this case, when we determine script R31, we have to put port 1 in the opposite state of its reference state, which means we have to open it. And now, with the response V not nulled, we follow the path of IT to determine script R31. IT first flows through R3 and creates a voltage drop across it. Then it flows entirely through R1, creating another voltage drop across R1. The sum of the voltage drops across R3 and R1 equals to V0, which has been nulled. So IT into R1 plus R3 equal to V0 has been nulled, has gone to 0. And the only way that can happen is for IT to have been nulled, which consequently means that script R31 given by Vt over IT is infinite. Now you wonder, how in the world did this happen? How did we null IT? Okay, it's been nulled, but how did that happen? Vt is sitting there. Well, you don't have to know exactly, but if you're interested, you follow the path of IT in the remaining part of the circuit, And you recognize that V0 equals to Vin plus Vt plus ITR2 equal to 0 when V0 is nulled, which means that IT in this branch is given by Vin plus Vt divided by R2. And in that case, the only way IT can be nulled is to make Vin equal and opposite to Vt, because V0 nulled, as we said, means according to this loop here, going around this way, look at it carefully, going around this way, the current IT is given by Vin plus Vt divided by R2. And the only way that current IT now can be nulled is to make Vt equal and opposite to Vin. You didn't have to do this, but if you were just interested in finding out, really, how did that happen, you can do it. Regardless, script R31 is infinite. And now we determine the null resistance looking into port 3 with port 2 in the opposite state of its reference state, as indicated here in the subscript. The reference state of port 2 is then open, so that in this case, when we put port 2 in the opposite state of its reference state, we have to short it. With the response V0 nulled and this port shorted, we recognize that Vt appears directly across the output V0, and with V0 nulled implies that Vt must equal to 0. That's the only way you can null V0 in this case, is to set Vt equal to 0. With Vt equal to 0, the null impedance looking into this port, Vt over It, will be 0. Recognize that It is non-zero because Vin is live and it is pumping current through R3, going through Vt, going to ground. If you want to know what that current is, it would be Vin minus Vt divided by R3, but who cares what that current is? It's finite, and Vt is 0, so script R32 is 0. And this completes the determination of the null resistances that go into the pairing of the extra elements in the numerator. When we substitute our results in the two-port terms of the numerator, we obtain R2 over infinity plus infinity over infinity plus 0. In the last term, script R2 was finite, but script R32 was 0, so their product is 0. In the first term, script R21 was finite, equal R2, while the script R1 was infinite, so R2 over infinity drops out, the last term drops out, and you're left with the middle term, which is of the form infinity over infinity, and that is indeterminate. But that can be resolved easily by changing the order in which we pair these two elements, or these two ports. In this case here that is shown, we are pairing 1 with 3. So we change that order, and this time we pair 3 with 1. So that instead of having this expression for the middle term, we're going to have this expression for the middle term. Script R3 is finite, and now we're going to determine script R13. And now we determine the null resistance looking into port 1 with port 3 in the opposite state of its reference state. The reference state of port 3 is an open, so in this case, when we determine script R13, we have to short port 3. Now, with the response V not null, let us say that there's a current I3 flowing through R3. which creates a voltage drop across I3, R3. That voltage drop, because the response is nulled, will appear directly across R1, and it will induce a current in R1 given by I3, R3 divided by R1. If we look at this current I3 and follow it through, we see that it goes through R2 and creates a voltage drop across it, R2, R3. If we look at this loop now, we recognize that Vt, the test voltage source, is given by the sum of the voltages across R3 and R2, which is I3 into R3 plus I3 into R2. The test current, on the other hand, It at this point, is the sum of this current I3 and I3 times I3 over R1. We write that down as well. And from these two, we can solve for the null resistance looking into port 1 with port 3 short as Vt over I3, I3's cancel, and we obtain R3 plus R2 divided by 1 plus R3 over R1. So the indeterminacy has been resolved in this form here. And we substitute for script R13 the result that we just obtained. And what we had earlier for R3 was R2 plus R3. These two cancel. And that ratio now turns out to be C3 over C1 into 1 plus R3 over R1. Hence, the contribution of the two-port terms in the numerator is going to be just this one here, which is C3 over C1 into 1 plus R3 over R1. And finally, we determine the last term of the numerator, in which all three impedance elements are taken together at the same time. The order in which we are taking them is Z1, Z2, Z3, and we have to determine now the null impedance looking into port 3 with ports 2 and 1 in the opposite states of their reference states. We have already shown that the first portion of this expression, SC2 script R21 divided by SC1 script R1, is 0. And we may be tempted to say that this term must disappear because it is multiplying a 0. But that is not the case we can show that script R321 is either 0 or is finite. Otherwise, if it's infinite, then you have 0 times infinity, and this whole term becomes indeterminate, and that will require you to change the order in which you're taking your impedance elements from 1, 2, 3 to 3, 1, 2, or 1, 3, 2 to resolve the indeterminacy. So, in this case, we're going to look for script R321 and check if it is finite. If it is finite, we're home free and this whole term disappears. To determine script R321, we look into port R3, but this time we're going to reverse the states of port 2 and 1 from their reference states. The reference state of port 1 was a short, and the reference state of port 2 was an open. So we have to now reverse that, and so we make port 1 an open circuit, and we make port 2 a short circuit, which results in this circuit now. In this case, you see that Vin has dropped out of the picture, and Vt itself is connected across to R1 and R3. And regardless of the voltage V0, which really is Vt, that ratio of Vt to It, which is the impedance seen by this test voltage source, is nothing more than R3, R1. Whatever you make the value of Vt, including 0, which is the null condition here, that impedance looking between these two terms here is always R1 plus R3. So R321 is R1 plus R3, regardless of what we make this voltage to be, including 0. When all the null resistances are substituted in the numerator, we obtain the complete expression of the numerator, shown here. We now move on to the denominator, in which we determine the various driving point port resistances, with the excitation Vin set equal to 0 as shown. In this circuit, we will determine the various port resistances R1, R2, R21, R31, R321, so on and so forth. We shall now see that all the driving point resistances are trivial and can be determined by inspection. Let us go to port 1 and determine the driving point resistance looking into port 1 while ports 2 and 3 are in their reference state. This can be seen to be given by R1. Now let us go to port 2 and determine the driving point resistance looking into port 2 while ports 1 and port 3 are in their reference states. Port 1 is a short, port 3 is an open. This resistance is seen to be given by R2 because R1 is shorted out by port 1 and R3 is into an open circuit. Now we can also see that the driving point resistance looking into port 2 while port 1 is in the opposite state of its reference state, that is to say an open circuit, is still given by R2. Let's go to port 3 and determine the driving point resistance looking into that port while port 1 is in its reference state a short and port 2 is in its reference state an open circuit. This can be seen to be given by R2 plus R3 because again R1 in this case is shorted out by port 1. Let's go to the driving point resistance looking into port 3, but this time with port 1 in its opposite state. And when we open port 1 and get it into its opposite state, we see that the driving point resistance looking into port 3 with port 1 in the opposite state of its reference state is given by R1 plus R2 plus R3. You can see that by following this line here, going through R2, turning around, going through R1, going through R3, and coming back here. Now, let's go to port 3 again, but this time we want to determine the driving point resistance looking into port 3 while port 2 is in its opposite state of its reference state and port 1 is in its reference state. So let's do that, and here we are. We're going to put port 1 in its reference state, a short circuit, port 2 in its reference, the opposite state of its reference state, which is a short, and determine R32. In this case, we see that R1 is shorted out, R2 is shorted out, so this is nothing more than R3. Finally, we look into R3 with 2 and 1 in the opposite states of their reference states. The reference state of port 2 was a short, so its opposite state is an open, and the reference state of port 1 is a short, so therefore its opposite state is an open. So we're going to open this and short this to determine R321. And there you go. Here we see that R2 is shorted out, and looking into port 3 with 1 open, we get R1 plus R3. And this completes all the necessary driving point resistances for the determination of the denominator, d of s, given by the 3 extra element theorem. And there you have it. You've determined the denominator of that transfer function completely by performing these 6 purely resistive calculations. You figured out the third order denominator by performing 6 simple resistive calculations. Now we substitute A0, N of S, and D of S in the 3 extra element theorem and obtain the desired transfer function AB of S. This is a bandpass type transfer function because we see that at high frequencies the S squared term in the denominator dominates while the S term in the numerator dominates, and hence the overall transfer function goes as 1 over S. It rolls off as 1 over F at high frequencies. The same is true as we go down in frequency, where in the numerator we see that the S term drops out and we are left with a constant, whereas in the denominator the S squared term drops out, the S term drops out, the constant stays, while the 1 over S C1 R1 goes to infinity and again knocks out the transfer function. So we do have a bandpass characteristics. What we want to do next is to determine the relationship between the various circuit components so that this bandpass characteristics admits a resonant type peaking at a given resonant frequency. With a bit of algebra, our transfer function can be written in this form, in which we define the following parameters. Now, if we can determine a relationship between the circuit components so that we get a pole zero cancellation in this transfer function, then it will reduce to a second order symmetric bandpass transfer function. And by symmetry we mean that AV of S over omega naught equals to AV of omega naught over S. This symmetry is with respect to the logarithmic frequency axis, because for a causal system we cannot have symmetry with respect to the natural frequency at any finite frequency. Be that as it may, we look for an additional relationship between the circuit components so that at the resonant frequency omega naught we have just a bit of peaking greater than unity. We now impose the symmetry condition on our transfer function. That is to say, we make AV of S over omega naught equal to AV omega naught over S. To determine AV of omega naught over S, we replace S over omega naught with omega naught over S in the expression of AV, and we obtain this expression here, which we compare and equate to the original expression of AV of S over omega naught. When we make these two expressions equal to each other, we recognize that we should have A2 equal to A1. That's our first condition. The second condition would be to make omega naught over omega naught prime equal to unity. That is to say, we make omega naught prime equals to omega naught. These are the two conditions which we are going to pursue in the next few slides to determine the relationship between the circuit elements which satisfy these conditions. When these two conditions are satisfied, the transfer function can be written as follows. In it, the denominator factors exactly into a quadratic and a pole that is equal to the zero, and we get the pole zero cancellation we were looking for. This will reduce the transfer function to a second order symmetric bandpass transfer function. This is what we were looking for. In the following expression of the second order resonant bandpass transfer function, we see that at S equals to j omega naught, the magnitude is AM over A minus 1, and the phase is 0. In what follows, we will determine how the circuit components should be chosen in order to make omega naught equal to omega naught prime and AM over A minus 1 greater than unity. We begin with omega naught and omega naught prime, whose respective expressions are given as follows. Now, looking at omega naught prime, we see here on the right-hand side that if the numerator and the denominator are equal to each other, then omega naught prime reduces to 1 over R2 C1. You look at omega 0, and you see here that if R2C1 was equal to R1C2 was equal to R3C3, then omega naught would also become equal to 1 over R2C1. So let's see what we got here. If I make C1 over C3 equal to R3 over R2, then I get C1 over C3 equals to R3 over R2, which means that I have R2C1 equal to R3C3. And that's here, R2C1 equals to R3C3. If I look at the next one, C2 over C3, and make it equal to R3 over R1, then I will have R1C2 equals to R3C3, which is here, R3C3 equals to R1C2. This means that if I make R2C1 equal to R1C2 equal to R3C3, then omega naught prime will reduce to 1 over R2C1 and will be equal to omega naught. We now determine A and AM from these two conditions that we just obtained. A can be determined either from A1 or A2, since those two are equal to each other. Starting with A1 and these two conditions, we obtain this expression. Starting with A2 and these two conditions, we obtain exactly the same thing. As for AM, with these two conditions, we obtain this expression. With A and AM determined, the peak value at resonance is now given by the following expression. In it, there are two independent ratios, namely C1 over C2 and C3 over C2, which we call alpha and beta. When we substitute for alpha and beta, we obtain the following expression for the peak. The peak here is seen to be a monotonically decreasing function of beta, so that its largest value occurs for beta equals to 0. Practically, we don't have to make beta equal to 0. We just make it much smaller than 1 plus alpha. Hence, with beta equal to 0 or very small, the peak now becomes equal to 1 plus alpha over alpha plus 1 over alpha. This function admits a maximum for alpha equals to 1 plus root 2, and the maximum value of the function is 1.2. We get this by setting the derivative of the function here with respect to alpha equal to 0. That gives us alpha max 1 plus root 2, and when we substitute in the function, we get a value of 1.2. This means that the circuit that we have has a maximum gain of 1.2 at the resonant frequency. To see how well this circuit works, we simulate it in LT-Spice, as shown here. In it, we have chosen the value of alpha, which is the ratio of C1 to C2 equal to R1 over R2, the value of alpha that results in the maximum gain, 1 plus root 2. So C1 is chosen to be 2.41 microfarads, while C2 is 1 microfarad. That's that ratio there. And R1 is chosen as 2.41, while R2 is 1K. So these two, their ratio satisfies the alpha maximum condition. Beta, which is the ratio of C3 to C2 and R1 to R3, that's supposed to be 0 ideally, but we can't make it 0. We'll make it about 100 times less than alpha, which is, I've chosen here to be 0.022. I've even loaded this circuit down with 10 meg and 1 meg to see how well it works. Well, with 10 meg loading, we look at that transfer function here, and we see that with 10 meg loading, the gain really reaches up to 1.2 as predicted. And with 1 meg loading, we expect it to be less, but we still get some gain, a little bit above 1.1 volts. So it works, and the resonant frequency is around 66 Hertz. Well, I hope you enjoyed this circuit.